Was wird daraus, wenn der Mono mal tot geht? Wo landen diese Sachen? Wo landen diese Instrumente? Was wird daraus?
Hello, everyone, and welcome to this week's workshop at the Information Security Club. This week we're going to be talking about hash functions, so if you've been itching to do some crypto, today's your day. A couple announcements before we get started. Next week is the fourth installment of our speaker series. We have Manny Hirthi, apologies if I messed that up, speaking on cyber supply chain risk. So make sure you get your club fees in if you want to come to that. And also, the end of reading break from the 25th to the 27th is made by CTF, so start getting excited for that. And yeah, I think that's all we have for announcements, so we'll get into the workshop. So first of all, make sure you fill out attendance. We need to keep track for membership, and you need to fill out attendance for at least half of our workshops to be a full voting member. So I will share that link and give you a couple of minutes or a minute, whatever, to do that. All right, so what we're going to be covering in this week's workshop. First off, we'll start with some of the basics of hash functions. So we'll talk about what hash functions are, then we'll talk about properties of secure hash functions, because secure hash functions are not necessarily the same thing. Resources. Sure, I will give you the link to the challenge files. I'll give it to you again later when we do the challenge, but I can paste it now. All right, so yeah, we'll start out with some of the basics, what hash functions are, what secure hash functions are, then we'll talk about birthday attacks, how those work, and what they mean for the security of hash functions. And then after some of that stuff, we'll get into some trickier things, well, slightly trickier anyway. We'll talk a bit more about how hash functions are actually designed, uh, how we actually construct them to make them secure, and then we'll talk about message authentication codes, or MACs, and how we can use hash functions in that, and also some attacks against those. So, for starters, hash functions. What is a hash function? Well, it deterministically maps inputs to fixed size outputs. So, what is this saying? Well, we have an input of any length and it maps it to some fixed size output. What does it mean that we're doing it deterministically? Well, this just means there's nothing random about how this happens. If we give a hash function the same input, it's always going to produce the exact same output. So, as an example hash function, we could have a hash function that takes the first letter of some string. And it doesn't matter what our string is. It could be the word potato. It could be 3/4 of the Declaration of Independence. Whatever size input we put in, it's going to hash to one letter, just the first letter of the string. This is an example of how a hash function might work. The important part here, if we have any input, no matter what size it is, the output is always the exact same length. So what are some more common examples of hash functions, or perhaps more relevant to security at least? Well, one hash function is MD5, which maps any input to a 128-bit output. Just like you see here, maps a string to a bunch of bits. SHA-1, again, similar thing, maps an input to a 160-bit output. And these are both not really secure hash functions, but sort of used that way sometimes, probably wrongly so. Some more secure examples, SHA-2, which is actually a family of hash functions. So there are a bunch of hash functions that are considered SHA-2 functions, and they just map inputs to outputs of different sizes. And SHA-3 is, again, the same thing. So how are hash functions used? Well, there are a bunch of places they're used. In particular, we're interested in security. There are a bunch of places outside of security you could also use them, but those aren't going to be our focus today. So one example is password storage. So for example, if we're keeping passwords, if our database gets compromised, we don't want attackers to have all the passwords of all our users, so we can hash them. So we can use it for password storage in that way. We can use it for proof of work. So we might get people to compute, for example, a pre-image of a hash. We'll talk about what that is later, so don't worry about it too much. And might use this, for example, to prevent denial of service attacks. You can get people that are making queries to your server to compute something involving hash functions, so they can't just spam your server. Another place this is used is crypto mining. So in cryptocurrencies, there's often some sort of challenge to do with hash functions. You have to prove that you did some work by computing some value. Message and file integrity. This is another place we can use hash functions. So, for example, download errors. We can detect those with hashes. If we compute the hash of a file we download and it doesn't match the hash that we were given, then we know there was an error in the download, because the same input should always give us the same output. We can use these as a part of digital signatures, so to prove who you actually are or who sent a message. And also message authentication codes, which are a similar thing. We'll talk about those later again. And also, again, I guess I have to mention it, blockchain. It's also used to make sure that things aren't changed in that. So how might we attack hashes? We haven't really talked about what makes them secure or not yet, but we'll just give you a bit of a brief warm-up. So in some cases, figuring out what the input to a hash function was is easy. Why might this be the case? Well, if a hash function is not secure, which again, we'll talk about what a secure hash function actually means later, then we might be able to easily figure out what the input was just by reversing the process. Also, if inputs are predictable, then we might be able to easily guess what a hash is. And there are a bunch of tools that attempt to do this, especially the predictable input thing, just guessing inputs and computing hashes to figure out what the input to a hash function was. And for more on that, you can check out our hash cracking workshop from last semester. But we're also going to do a short warm-up that will allow you to crack some hashes. So I have two hashes here. These are the output from some hash functions. And you'll want to try to compute the output of these. And my hint is just look for hash crackers online and see what you can find. And I will give you those hashes because I don't expect you to type all that out. Yeah, I will give you a couple of minutes to work on it. I'm also going to apologize right now because those flags have not been added to Orchid yet. I will do that shortly. Um, Another note, if you get the flags, please DM them to Orchid, our Discord server. It's a bot. It will give you points for the flags. Please do not send them in the public chat. Do not share the flags, please. And I think, yeah, okay. I think we will go through this now. So there's nothing too crazy going on here. All I'm going to do is I'm going to search for hash crackers. And I'm just going to pick the first result that comes up here based on my two hashes. And I'm going to crack, and pretty much instantly it gives us the result of these. One's an MD5 hash, one's a SHA-1. And the reason it was able to do this so quickly is probably because, well, these are easily guessable inputs. They're just dictionary words. probably just had a dictionary of words and hashes computed on those words. So it was just able to find these right away. Okay, so we talked about what hash functions are, but what are secure hash functions? What's the difference? What actually makes something secure? Well, for a hash function to be considered secure, it should have, in particular, three properties. These three properties are first, preimage resistance, weak collision resistance, and strong collision resistance, which we will talk about what these actually are right away. But to be considered secure, a hash function should have all three of these properties. So first, preimage resistance. Given a hash h, it is difficult to find an input m such that hash of m equals h. So what this is saying is that if we have some output from a hash function, we shouldn't be able to find anything, any input that actually produced that output. That should be too difficult for us to do. So as an example, let's go back to this first letter hash function that we have. And now I will ask the chat and awkwardly wait here. Does this first letter hash function that just takes the first letter of a string, does this have preimage resistance? So that we can not find an input that will give us some specific output. I will awkwardly wait for an answer. And I see one person saying no, and yeah, that's correct. It does not have preimage resistance. If we have some output, we say A, then we can just easily take any string, any word, whatever, that starts with an A, and we know that's going to have that output. So it's very easy to find a preimage for this particular hash function. So it doesn't have this property. So second property is second preimage resistance or weak collision resistance. So this is given an input m, it is difficult to find another input m2 where hash of m equals hash of m2. So what this is saying is if we have some value, we shouldn't be able to find any other value that's going to hash to the same thing as that. So again, we'll do another example with our first letter hash function that just takes the first letter of a string. Does this have weak collision resistance? Does it have this property? Again, I will wait for an answer. Okay. So we have a few people saying no. That's correct. We have another person saying they don't see the difference from the last property. So the last one, if we have a hash, we shouldn't be able to find something, any input that's going to result in that hash. With this one, we're not given a hash to start with. We're given an actual input, and we're not supposed to be able to find another input results in the same hash. And these do look somewhat similar. The reason, like, this one's called preimage resistance. This one, another name for it is second preimage resistance. So they do look similar, but one we're given a hash and one we're given another input. So yeah, and as people are saying, no, that's correct. If we have some input, say we just have word apple, well, we know the hash of that is going to be A. we can easily just choose another word that starts with an A, and we found this collision. So no, this hash function doesn't have this property. And now we have one more property, so strong collision resistance. It's difficult to find two different inputs, M1 and M2, such that hash of M1 equals hash of M2. So what this is saying is, well, basically just that. We shouldn't be able to find two different inputs that hash to the same thing. Now, this does seem slightly similar to the last property. Again, the difference is with this property, we're given some fixed input. With this new strong collision resistance, we don't have any fixed input. We can do whatever we want. We can just choose any two inputs and try to get them to hash to the same thing. We're not restricted to any particular input. So again, we'll go back to our first letter hash function one more time. Does this have strong collision resistance? And again, you have some people saying, no, it doesn't. And that's correct. This definitely does not have strong collision resistance. We can just choose any two strings that have the same first letter, and they're going to hash to the same thing. So again, it's easy to find two inputs with the same hash. So going off this last property, we're going to look at something called birthday attacks. So question here, so do two people here in this workshop share a birthday? We have about 20 people here. Now, I could wait for an answer, but I'm not going to, because there's probably a math nerd here who knows the answer, and that would ruin the punchline. But we have about 20 people here. There are 365 days in a year. It seems like there's a lot of days, not a lot of people. There's probably not two people with the same birthday. But it turns out the odds are actually pretty high. In particular, this is the odds of two people sharing a birthday. Now, this looks kind of intimidating. There's this formula with factorials and exponentials. This isn't actually too difficult to derive if you know some statistics, but we're not going to worry about that, and we're not going to worry about the derivation. It's not terribly important for what we're doing, but basically this is a probability that two people, given a group of n people, share a birthday. And if we were to just plug in values for n for the number of people in our group, it turns out with just 23 people, there's already a more than 50% chance that two people share a birthday, which is actually pretty high. There are 365 days, only 23 people, and yet there's still more than a 50% chance that two people share the same birthday. And it turns out that we can actually generalize this idea to hash functions. So this formula is very similar, except that now we're imagining our number of days isn't fixed to 365. We could have a year with, say, 100,000 days or whatever. So if we have d days, we have n people. This formula is, again, going to give us a probability, pretty much the same formula as before. Adapting this to hash functions, we can think of d as the number of possible outputs from our hash function, and then n is the number of hashes we've computed. So if we have d possible hash outputs, and we compute n hashes, this will give us the probability of two hashes being the same. And again, this is very similar to, if we just plug in values, very similar to what we found on the last slide, that there's about a 50% chance of two hashes being the same, with a value of n that's about 1.25 times the square root of d, which, going back to this, the square root of 365 is, what would that be? For a bit less than 20. So just a bit more than 20 is threshold where we have about a 50% chance. So about the same here. So it turns out that we only need to compute about the square root of the number of possible hashes to find a hash collision with a fairly high probability. And this is known as a birthday attack. So again, if we have, if we have an n-bit hash function, so it produces an output of n bits, there are going to be 2 to the n possible outputs. Just counting each bit can be 1 or a 0, so we multiply that by the number of bits. We have 2 to the n is the number of possible outputs with an n-bit hash function. So with about 2 to the power of n over 2, that's just the square root of 2 to the n. If we compute that many random inputs, then there's about a 50% chance of a collision in their hashes. And one more thing, just kind of a tangent here, closely related tangent, is we haven't actually, we said that these properties, it should be difficult to do something. It should be difficult to find a preimage or difficult to find a collision, but we didn't really describe what difficult is. It's not clear exactly where the line is between something being considered easy to do and something being considered difficult to do. And so we can describe this mathematically. Basically, we're going to describe the security level as b bits, where 2 to the b is the number of guesses to break something. So for example, this might be if it takes 2 to the b guesses to find a preimage to a hash function, then it'd have b bits of security. Or if we have to compute 2 to the b hashes to find a collision, then it'll have b bits of security. And this is related to, there's a more formal mathematical way of describing this called entropy, which there's an entire 4th year course on that, Computer Science 530. So if you don't know what that is, don't worry about it too much. Turns out this idea of just being number of guesses we need to break something is a reasonably good description for our sake. And also we can apply this to things besides hash functions, other cryptographic primitives. But yeah, we'll just be focusing on hash functions. So if we need 2 to the b guesses to break our hash function, finding a preimage or collision, then we'll say it has b bits of security. So given this last birthday attack that we talked about, we know that if we have an n-bit hash function, we will probably find a collision after computing about 2 to the n over 2 hashes. So that means that the security of a hash function, just based on this attack alone, can be at most n over 2 bits. And there could be other attacks that make it even worse, but this is the best security a hash function can have. And sort of the line that's considered the dividing point between easy and difficult, you could say is 112 bits of security. This is kind of the standard. If it has 112 bits of security, it's considered secure. And I believe this is set to go up to 128 bits by 2030 or something like that. So yeah, that's just kind of the standard for now, is 112 bits of security. So going back to some of these hash functions that we mentioned before and what we know now, how secure are they? Well, if we think about MD5, we know this produces a 128-bit hash output, and it can have as most half of this as its security level. So the 128-bit hash, we take half of that. We have a maximum of 64 bits of security. And remember, we need 112 to be considered reasonably secure. So this is clearly not secure. This is quite a bit less. Again, if we look at SHA-1, we have 160-bit output, which means there's at most 80 bits of security, which again is not enough to be considered secure. Just looking at the chat here. Why 112 in particular? I'm not sure exactly what computations go into that number, but basically it's just based on the idea of how much computing power is reasonably available to someone who's really well funded, say a government or whatever. And then we just choose a value that's basically too much for them to practically compute. And I believe, I don't know the exact what goes into the exact computation of 112, but I believe that's about the standard right now. Okay, so back to this. So yeah, we see that MD5 and SHA-1 have much less maximum level of security than what we would consider secure. And it turns out they actually have less security than this due to other attacks that we're not going to talk about today. So this level here, just dividing the output by 2, this is just an upper bound on the level of security. It doesn't guarantee we actually have that much. It's just the maximum we could possibly have. Moving on to SHA-2. SHA-2, remember this is a family of hash functions again, so they have different output lengths, but all of them are at least 224 bits in length, which means they have an upper bound on their security of at least 112 bits based on this attack. So if there's no other attacks against them, maybe they're secure, maybe not. We'd have to do more analysis to figure this out. And again, SHA-3 is similar lengths to this, so possibly secure. Okay, so now we're actually going to carry out a birthday attack. Not against an entire hash function, but against part of one. What we're going to want to do is find two values, two strings that have the same first byte in their SHA-256 hash, the first byte being the first 2 hex digits. Just to give you an example of how you might go about this. So if I wanted to compute the hash of something, I could just do echo-n, and this just ensures that I'm not going to print out a new line, which will change the hash value. So if I want to hash the string one, this isn't the number one, it's the string. We output that from this echo command into SHA-256, and this is just going to give us a SHA-256 hash. And if we wanted to find something with the same first byte in its hash, we could just compute values, look at the first byte, it's D4, well, that's not the same as that. We compute the hash of 3, again, compare it against these hashes, and we don't see a match, so we could just keep going like that to try to find 2 strings that have the same hash. And there's not really any tricks here. It's pretty much just as simple as computing hashes. From what we've learned, we'll probably run into something fairly soon. And yeah, I'll give you a few minutes to just try doing that. Try to find 2 things, same hash. When you do, you can connect to this program here. You just netcat into this IP, and it will ask you for your 2 strings. If the first byte matches, it will give you a flag. And I will give you a few minutes for that. All right. How's everyone feeling about this challenge? Maybe I'll do this. Seems to work well. Say like 1 being I have no clue what is going on. 10 being is it actually helpful? I mean, it's kind of just an exercise. And yeah, I guess it depends how much you're actually familiar with this. But yeah, it's more or less an exercise. But still, okay. You have one person saying one. Yeah, I think we'll go through this and move on. So, how do we actually compute this? Well, we can just keep going on. Keep going with the same process I have here. So if I compute more values, 4, 5, still no matches. But I can compute the hash of 6, still none of these have the same first 2 characters. And we could just keep going, and I'm going to cheat here because I've done this before. When we hit 12, we see that these first 2 bytes, or, well, the first byte, first 2 hex characters, are the same for the string 1 and the string 12. Now, this only took us 12 attempts to get here, so that seems awfully fast. What's actually going on? Well, remember, this is a birthday attack we talked about. Yes, for 1 byte, there's 8 bits, so there's 2 to the 8, or 256 possible values. And yet, in just 12 guesses, we already found a collision in these first 2 hex characters. Yeah, so didn't think to use numbers. Yeah, in reality, it doesn't even matter what you use. We could just choose random values and put them in, and we'd still get a similar result. It might take us a few more attempts or something, but yeah, so with just 12 guesses, we've already found a collision, even though there are 256 possible values. Well, the square root of 256 is only 16, which is about what we calculated before. The square root of the number of values, we're probably close to a 50% chance of collision. So with a number of guesses is just less than the square root of the number of possible bytes, we already found a collision. So that just shows that though there are a large number of outputs, the number of guesses it's actually going to take to find a collision is much smaller than that using this attack. And in case anyone wasn't sure about submitting that, just gonna move that. Yeah, if I just connect to this with netcat, I can enter in my 2 strings. If the same first byte, it will give me a flag. So yeah, that's a challenge. Basically, like someone said, there's not anything tricky going on here. It's just showing that in reality, brute forcing a hash isn't actually as hard as it seems like it should be with the number of possible hashes. It takes substantially fewer inputs to find a collision. Okay, so now we'll move on from this and we'll get into how hash functions are actually designed to achieve these security properties. So first thing we're going to need to build a hash function is something called a compression function. Now, there are multiple ways to design hash functions. This is used in a lot of them, however. So what a compression function is it's a function that maps 2 fixed size inputs to a fixed sized output. And it should have all of the security properties we previously mentioned. So now you might be wondering, wait a minute, what's going on? To make a hash function, we're going to build it out of hash functions. How is that useful? We kind of have a problem here. Well, it turns out that since rather than having an arbitrary sized input to produce a fixed size output, we have a fixed size input to produce a fixed size output, and we can handle this differently. So we don't need to do quite the same thing as a hash function. We just need some way to map these inputs, these fixed size inputs, to an output in some way that's hard to figure out what the inputs were and hard to get collisions. And how we do this is we can use a principle known as confusion and diffusion. Basically, this means we're going to be applying a bunch of substitution and transposition ciphers repeatedly. So basically just replacing values in the inputs with other values and then moving them around. And we do that a bunch of times. And if we do it properly, which is not necessarily actually that easy, but if we do it properly, then it will achieve properties similar to the ones we've seen. And quite often this is done using block ciphers. Now, if we do that, we have to be careful because block ciphers are ciphers. They're meant to be decrypted, which means they're reversible. And we don't want it to be possible to find preimages of this, so we don't want something reversible here. So if we do use a block cipher, we'd have to be careful about how we did that. So I found a way to generate random strings of characters for the last one. Yeah, there are lots of ways to do it, but it turns out you can just count up sequentially, and that also works. So yeah, this is a compression function. This is basically the building block of hash functions, the way we're going to look at. And now how we're going to use these compression functions is using something called the Merkle-Damgard construction. And it's going to look like this. Might look a little bit scary. We're going to break down what this means. This is the design that's used for MD5, SHA-1, and SHA-2. So a lot of common hash functions use this Merkle-Damgard construction with compression functions. And this is why we're focusing on this particular design for hash functions. So how this works is we take our input, which remember can just be an arbitrary size. And what we're going to do is we're going to break this up into blocks of some fixed size, because remember we need fixed size inputs to our compression function. And now this input, it can be any size. It might not necessarily be a multiple of the size that we need for the compression function. So we can also add some padding to the input to make it the correct size. So we add the padding to the input. We break it up into blocks of the size we need for our compression function. Now what we do is we just take some fixed initialization vector, which this isn't a random value. It has to be fixed because we need to get the same output every time we compute the hash function. So we take this value. That's one of the inputs to our compression function. And then a block of the input will be the other input to the compression function. We compute that. We take the output from the compression function, and then we feed that back into the function as one of the inputs. And the other input is going to be the next block of our actual input message, or whatever it is. And then, again, we take the output of that out of the compression function. That's one of our inputs. The next block of the input is our other input to the compression function. We compute that again. We just go on repeating this process, feeding the output of the compression function back into itself along with another block from the input until we run out of input. And then the final output from a compression function is our actual hash. And this entire thing is how our actual hash function is going to work. Basically, it's just chopping up the input and applying this compression function repeatedly. So now we're going to change gears. Yes, bottom left rectangle. This says IV. That just stands for initialization vector. It's just some initial value. It'll just be some fixed string of bytes. It'll depend on the hash function what this actually is, but it's just some initial value that we need for the first input into the compression function. Okay, so changing gears a little bit, talk about message authentication codes. So what are these? Well, they're used to verify the sender and message integrity. So if you send a message, you don't necessarily know who that message is from. Has it been tampered with? To deal with that, you can use a message authentication code, which is essentially just going to tell us that, in fact, this message is valid, it hasn't been tampered with, and the sender is who you think it is. And how this works is it's going to map a message and a secret to some tag value. And the secret should be shared between the sender and receiver of the message, and nobody else should know this, so that we can actually confirm that the person we're getting this from is the person we think it is. So we pass the secret and message into our MAC, our message authentication code, and we compute a tag. And to verify this, the receiver would just take that message, again, pass in that shared secret they know, and recompute it, make sure that the tag matches the one that was sent to them with the message, and that's how they verify this is correct. So what properties should this have? Well, first of all, it should be hard to compute without the secret. Obviously, if someone could compute a message authentication code without knowing the secret value, it's not really providing any authentication. It could just be anyone who created this MAC. So it should be hard to compute this without the secret. And it should also be hard to compute given any number of message and tag pairs. We shouldn't be able to compute the MAC for a different message. Of course, the same one, we already have a tag, so we can compute that. But for a different message, it shouldn't be possible to do that. Again, if an attacker was able to just see some transmissions and then create a MAC for a message, that could be a problem. It's not really what we want. So these are sort of the two properties we need for a MAC. And now, how do we actually design a MAC? Well, if we look at this, we're just taking some inputs, we're producing an output that's hard to determine what the inputs are. I mean, this looks a lot like just a hash function. So we could just take our secret, our message, concatenate them together, run them through a hash function, and call that the tag for a MAC. So this is one way we might try to build a MAC. Is this a good idea? Well, it turns out it's not, as we'll see shortly. So let's look at how this actually works internally. So if we were to just take our secret, append it to our message, pass this into our hash function, assuming it's a Merkle-Damgard hash function, as a lot of hash functions are, this is what it's going to look like internally. So we add our padding, and then we chop the secret, and followed by the message up into blocks. We just pass it into our compression function, and we compute the tag like this. Now, do we see any problems with this? It's probably not obvious what the issue is here. But what if we were to just add on to this message? What could we do with that? Well, there's not really anything special happening at the end here. The hash function is just repeated applications of the compression function. So if we were to just compute the compression function again with the hash, which is just the output from the compression function, like all the other previous inputs were, it's basically just adding on to the hash. So if we take our malicious block that we want to add on to this message, we add it to this message, we add it to the secret, the message, and the padding, we add this evil block on, and we just compute the compression function with this tag value as one of the inputs, our evil malicious block that we added onto the message as the second input. That'll just give us a valid hash, as if we just hash this entire thing, the secret, the message, the padding that was added, and this block. So to show this in a more formulaic way rather than the picture, the hash of the secret plus the message plus this padding value, because of course that's taken into account in this compression function here, and then this added block, if we were to put those all together and hash them, assuming they're the right length, because we've accounted for padding, both the padding that was in the original hash and in our block. If we were just run that through the compression functions or hash that, it's going to be the exact same thing as if we were to just run the compression function on the hash of the original message we have here and this block that we've added. And this is a length extension attack. And now we're going to actually carry out a length extension attack. So there's quite a bit going on here. I'll try to go through the files that I'm going to give to you, and yeah, we'll do that next. Actually, I will share the link to those files first here. These are the same files that were posted earlier. I'm just sharing them again for anyone who missed those. Okay, so let's look at what files were actually given. So first we have a hash function. So what does this hash function look like? Well, it's built from a compression function, like what we've been talking about. What this compression function does is it takes in two input values, which are just bytes objects in Python. And these are going to be 32-byte values that we take in. And so all this compression function does is just concatenate these together, run SHA-256 on them, which obviously I'm using a hash function as a compression function, which wouldn't do in practice, but it's simpler for this particular case. So yeah, basically this is just a compression function, exactly like we talked about before. That's the building block of the hash function. It's going to take in some previous input, like the IV or output from a previous compression function, a block from our input, and it's just going to jumble them up in some way to produce another output. And how does our actual hash function work? Well, first it's going to take our message, pad it so that it's a multiple of 32 bytes in length, because we need to have the right size for the compression function, and it's just going to pad it with space characters. And then it's just going to set some IV, which in this case is all zeros, and it's just going to repeatedly run this compression function using the Merkle-Damgard construction like we just saw. It'll take this IV, take in each block from the input, run the compression function on that, run the compression function again on the previous compression function output and the next block from the input, and it'll just repeat that to get the actual hash. So that's how this hash function works. Basically, the important parts to note for you, it's being padded with spaces. The blocks are 32 bytes in length. Keep that in mind. Next, we'll look at the actual server that you're going to be interacting with. So what this does is it has some secret value, which is 32 bytes long, even though you don't know the value. You can send in a request and a message authentication code for that request. And what it's going to do is it's just going to use the map we discussed just before. It's going to take the secret. It's going to append that to this message that you send, this request string, and it's going to compare it to the map that you sent to make sure that it's correct. If it is, it'll just do the commands it has. It can either show a greeting or show a flag. So you'll need to send a message with a valid MAC that contains this string show flag in order to get it to actually print the flag. And you have one last thing, which is a message and tag that were captured. So this is a request string that was sent to the server. Just show greeting, and we have this message authentication code for it. So I'm just going to show this on the server. That's our IP here. Okay, so if we connect to this, we're going to enter show greeting and then Mac, which is just the string of hex characters, no 0x or anything in front of it. Send this to the server. It's a valid Mac for this request, so it prints hello world. And to actually see the flag, we're going to want to append show flag onto this message using a link extension attack like we looked at earlier. And that's going to be your goal for this challenge. I'm also going to give you a link to the slides in case you want to look back at some of those diagrams. You might find that helpful. Yeah, so your goal is to carry out this attack to get the flag. This challenge might be a bit trickier, so I definitely encourage you to work together on this in the Discord, ask questions, whatever you need to do. Yeah, I think that's about all I can give you for now. So I think, yeah, I'll give you probably at least like 20 minutes to work on this, maybe longer or less if people are having an easy time with it. So yeah, I will give you a while to work on this. realizing I did not go through how to actually use some of these Python functions in case you're unfamiliar with them. So I think I will go through how to use a couple of those and maybe give you uh, a hint or two about how we might go about this. So you probably want to use the compression function from this myhash file that you were given. So to do that, you want to import this myhash module just like that. Just import myhash file name. Then compute this compression function. You need to pass it two arguments, which are bytes. So to do that, you have to have a B and then quotes to denote a byte string. If you're just entering it in as raw value. So I could enter in things like that, and this is going to give me an error because I need to make sure that those are actually 32 bytes in length. So if I pass in two arguments like that, it's just going to create the hash function with those two inputs, or the compression function rather. To compute the values you're given, to convert these to bytes, so if I was given this hex value here, and I wanted that as bytes, what I could do is I could use the I believe it's from hex. Use this bytes from hex function on just a string of hex. It'll convert it to a bytes object that I can pass in its compression function. So I'm just going to take this value as my original Mac. If I wanted to pass this into the compression function, which you might want to do, I could just convert this from hex to bytes, pass that in as the first argument. Because remember, we're trying to compute the compression function on the previous hash value, and then there will be some block that we want to add that's going to contain show flag. And this is going to give us a hash that contains show flag appended to something, which is going to look a lot like the original message. But there is going to be something else in there. So you have to remember you can't just hash the message. It's not the right length to start with. And also, if you want to compute the hex string from these bytes, you could just take a bytes object like that and call this .hex method. And that'll return the hex for a bytes object. Again, I will give you some more time to work on this. All right, you've been at this for a while. I see some people maybe having difficulties. The server still seems to be working, from what I can tell. I don't see anything wrong with it. So, do we want a little bit more time to work on this, or are we giving up? But what's the general feeling about this? Does anyone have any questions? Anyone giving up? Anyone want more time? Okay, a couple of people want some more time. Give it a few more minutes then. All right. I guess we're getting close to 8 years, so looks like a couple people have solved it. Let's go through how we can do this. So, I'm just going to put both on here to work things out. So, let's look at our original message here. So, we have our original message is show greeting. And then the MAC for this message is that. And we'll convert it to bytes. Okay, so this is our original message and MAC that we've captured. Now, remember that we can't just directly put this value into the compression function because it needs to be a multiple of 32 bytes in length, or for one input of the compression function, it needs to be exactly 32 bytes. So we're going to take 32, we're going to subtract the length of this original message. Gives us 19. So we're going to need to add 19 bytes of padding, or 19 spaces, onto this original message to determine what was actually computed in the process of computing this MAC. So our original is actually going to be original plus 19 spaces. So after padding, this is what was actually run through the compression function when the MAC for that message that were given in the log file was computed. So now we want to add something onto this. We want to add show flag onto this. So now we need to determine what our added block is going to be. So we know it's going to start with show flag. But again, we have to have a full block to pass into the compression function. So we're going to need to make this a multiple of 32, well, exactly 32 bytes in length to pass into the compression function. So again, we'll take 32 minus the length of this thing we're adding. It's 23, so we're going to need to pad this with 23 spaces. So we take this, we add spaces. So this is going to be what we're passing into the compression function to actually compute. So now I'm going to import a hash function. And I want to take this original MAC and then this block that I'm going to add, and I'm going to compute the compression function on that. And this is going to be my new MAC. So why is this the case? Just go back to this diagram. So remember that basically this our hash function just works by computing the compression function on blocks in the input. So by taking our original input, which was concatenated to the secret before actually computing the hash. So if we add the padding to make this a multiple of 32 bytes in length, and we don't need to worry about the length of the secret for that because it's already 32 bytes that's given in the file. So we just need to make this message and the padding a multiple of 32 bytes in length. So we have, go back here. this thing with the secret appended at the front, this is the thing that was actually passed through the compression function a few times to get the original hash. So our original MAC is this tag value here. That's our message and padding. We don't know what the secret is. And then our evil block that we're adding on is this add value, the show flag and then spaces. And we need to take account that if we were to pass show flag into the hash function, it would pad it with spaces. So if we just take our original MAC, we pass it in as one input, this block is the other, that's going to give us our tag for a new message that is now the secret, the message, the padding from the original one, plus the block we added, which also contains some padding. So then the actual thing, the actual message we want is we pass this as our message to the server, so the show greeting and the show flag with this is our hash. This should be a valid MAC for this string. And we can do this with or without the spaces in this case. It won't matter because remember before the compression function is actually computed, it's going to tack these spaces on as padding. So we could just pass this thing into our server. So we'll take our message. Send server request. Then our MAC is just the result of the compression function on the original MAC and the block that we added with padding. And that's going to print our greeting and the flag. That's a valid MAC for that. And that's how we can carry out a length extension attack. So one last note on this. How do we actually deal with this problem of length extension attacks? Well, there are a few ways we can do this. One is we could do a similar thing, but we could use truncated SHA-2, which is basically what we're just going to do is we're going to compute a SHA-2 hash, and we're just going to chop off the last few bits or whatever so that we can actually use it to carry out this attack because we don't have the entire output from the compression function to pass into the next one. Or we could use SHA-3, which does not use this Merkle-Damgard construction. It's designed in a different way, so it's not vulnerable to this. Kind of another common way is to use HMAC, which is computed using this ugly-looking formula where we concatenate and XOR things and run it through our hash function multiple times, and this way we can compute a MAC that's not actually vulnerable to this length extension attack. And a note about why this was actually a problem. It's not that our hash function is necessarily insecure. The problem is we're asking a hash function to do something that it never promised. Because here we're given a message tag pair and we find a tag for another message, but that's not something that was one of our security properties. We weren't supposed to be able to find pre-images, and we didn't. We still don't know what the actual secret that was used was. We never found a collision. We didn't compute two things that had the same hash. We just found the hash of something else given a different hash, basically, which is not necessarily something that's supposed to be hard. We are supposed to be able to compute hashes usually relatively easily. So yeah, it's just that we were misusing the hash function in this case, and that was our problem. And that's all I have for this workshop. So reminder, again, we have our speaker series next week. Make by CTF is coming up, so get excited for those. Don't forget about them. And yeah, thanks for coming to the workshop. That's all for tonight. Good night, everyone.